So I mentioned that we were going to talk about this method of separation of variables. That's what this section is about, and then we have a couple of applications that go along with that. But basically, it just says if you have what's called a separable differential equation, then you should be able to write it as a product of a function of x and a function of y. Okay. For example, here is a separable differential equation. Because, and I think this is hopefully pretty obvious, that this is the function of x and this is the function of y. So this is like your g of x, and then this is like your f of y. So as long as you can have your differential equation written in such a way that it's a product of a function of x and a function of y, then that is considered a separable differential equation. If you can't write it in this way, it's not separable and you have to do something else. But of course, in this section, that's all we're going to see is separable differential equations. Okay, and then when they are separable, you can separate them just like we did with that one with the population growth model. You can put all the y's and the dy's on the same side. You can put all the x's and the dx's on the other side. You see what I did? I just divided both sides by y, and I multiplied both sides by dx. Okay? Then that produces what almost looks like two integrals, and in fact, all you have to do to make it two integrals is just do this. Put your integration symbols there, and then integrate both sides with respect to the variables that you see. So on the left side, we have dy over y integral. We've seen that that is ln y. Really, it's ln absolute value y. I'm going to just kind of neglect that for now. But the other side, raising that to the third power and then dividing by 3, we're just going to get x to the third. And don't forget, we always have to have this constant of integration. And I pretty much always start out by putting a C1, and then we're going to change the constants just like we did on that last one. So we need to solve this for y, make e the base. Is it supposed to be y squared? Oh crap, it is supposed to be y squared. I miscopied it. Yeah, that's going to change things a bit. Yeah, so now let's just do the left side this way. Y to the minus 2 dy. That's going to be negative y to the negative 1, right? And then the right side is x to the third. All right, so yeah, just picking up from where before we lost connection. Yeah, integrate the left side, you get negative y to the negative 1. Integrate the right side, you get x to the third. So after we do that integration, we're going to get this equation. Negative y to the negative 1 is equal to x to the third plus some constant c. And again, I'm going to call this, in this case, I don't know if yeah, let's just call it c1. Now I just need to solve this for y. That's the last step here. So I'm going to rewrite this as 1 over y, and I'm going to distribute that to both, I'm going to multiply both sides by negative 1. So I'll get negative x to the third. I'm going to go ahead and call this a new constant. I'm going to call it plus c, where c is equal to negative c1. Okay, and remember, with constants, we can always do this. If we want to always stick with having just a regular c there, if it's just another constant, we can always change it. Okay. Then I'm just going to, the quick way to do this would be we would multiply both sides by y, and then we would divide by negative x to the third plus c, or what we can really do is just flip both sides of this equation over. If I flip the left side over, I just get y. If I flip the right side over, I get this, 1 over c minus x to the third power. And so that is actually what's called the general solution to this differential equation. Now, when would we be able to, why is it called a general solution? Because that c there, right? That c is the thing that's making it a general solution. In fact, I kind of forgot that I was going to mention something else. We skipped over section 9.3, if you saw that. Sorry, 9.2. That section is about what's called slope fields. And I think next time I'm going to talk a little bit more about slope fields because they are kind of important. What a slope field is it's generated by the differential equation itself. I don't think we have time to go through too much of that, but Desmos has this really cool thing where we can actually see slope fields. We don't have to actually graph them by hand. They're kind of a pain. But really what a slope field is just telling you, like, if you were to plot the solution curve on a slope field, you would find that any solution curve has to follow the slope field. And so when I say this is the general solution, well, of course, that C could be anything that you want it to be, right? And if I change the C's, then I'm going to get a different solution, right? But all the solutions are going to kind of roughly look the same, right? If I change C a little bit, it's not going to change the solution that much. But how would we figure out what that C is? Well, we would need some other piece of information. And that's why we have initial value problems, right? If I were to also tell you, for example, let's say y of 0 is equal to 1, well, what could I do? Then I could plug in 1 here for x, and I could plug, or I'm sorry, 0 for x, plug in 0 there, plug in 1 here, and then that would allow me to solve for c. And then I would have what's called a particular solution to the differential equation, if you see what I mean. So if you have an initial value also, then you can figure out what that c is. So next time we'll talk about slope fields a little bit, and then we'll continue on with these, and then we'll do the word problems on the other side here, which these can be kind of tricky. Particularly, I think the mixture problems are the ones that students don't really like very much. They are kind of hard. The orthogonal trajectory problems are actually very cool if you kind of get what's happening with them. They are pretty interesting. So are the mixture problems. They're just a little bit harder to deal with. So we'll talk about that stuff next time. So I think we just did the first example. Let's go ahead and just keep going on that. Okay, so again, remember for the separable equations, we just want to make sure that everything that has one variable is on one side and everything with the other variables on the other side. So in this case, theta and t are the variables, so we'll multiply both sides by theta and divide by secant theta. But you divide by secant, it's the same as multiplying by cosine, so really we're going to end up with cosine on the left there. And then we've still got the d theta on the left. And then on the right side, we'll just multiply by dt. So we're going to be left with dt over, oh, t dt actually, sorry, t dt. Let me redo that. Over e to the t squared. Okay, so that's just a bit of algebra, moving stuff around, getting all the t's and the dt's to the same side, thetas and d thetas to the other side. So then at this point, we put the integration symbol in front of both sides, integrate both sides. So here we'll have to remember some stuff from the last exam. That left side integral requires integration by parts. We'll do u equals theta, dv equals cosine theta, theta, du is d theta, and v is sine theta. So the parts formula says this will then become theta sine theta minus the integral v du, so that's just going to be integral of sine theta. And so that becomes theta sine theta. The antiderivative of sine is negative cosine, so this becomes plus cosine theta. Okay, then for the right side integral, we'll just have to do a substitution on that one. For that, we can say that u is equal to t squared, du, 2t, dt. Divide both sides by 2, we get 1/2 du is equal to t dt. And so that's what we see in the numerator there, t dt. That's going to become 1/2 du. That was the u there, so we're going to get e to the power of u there. Okay, so our new integral will be 1/2 du over e to the u. And then you can rewrite that if you want to as e to the minus u du. And the antiderivative there will be negative 1/2 e to the negative u. And then we can rewrite that as negative 1/2 e to the negative t squared. Or if you want to write that with positive exponents, you can write it as -1 over 2 e to the t squared. All right, so that's integrating both sides. Now we'll just come back to the original equation there where we had separated it. And so on the left side, we have our first integral of theta sine theta plus cosine theta is equal to -1 over 2 e to the t squared, and then we'll just add our constant of integration. Remember that constant takes care of both of the constants that we get for the left side integral and for the right side integral. All right, so now if we notice what we did on that first problem is we actually tried to solve it for y equals some function of x in that first problem. Here the dependent variable is theta and the independent variable is t, but if you look at this equation, there's really no hope of solving this thing for theta, right? That's not going to happen. Okay, so if it's not possible to solve for the dependent variable in terms of the independent one, you don't have to. You can just leave it as an implicitly defined function like we have here. So this thing here that I've written on the bottom line, that's the solution to this differential equation. All right, now I wanted to also, I just remembered I wanted to show you guys a little bit about slope fields. So let me see, I guess we could use this example. I don't know, I think maybe the previous problem was better to use as an example to show kind of what a slope field is. Because this differential equation is going to produce a pretty wild looking slope field. But maybe that's okay, I don't know, let's see. I'm going to go ahead and find Desmos and I'll share that with you in just a second. You can see that it already has a slope field on here. Everybody see what I'm talking about there? So what a slope field actually is, you have a differential equation. In fact, let me let's do the same one that we're looking at right here. It says g of x is equal to 2x over y. You can kind of see what it's doing here, what those little lines are. Maybe by hand, I'll just show you kind of where they're coming up with that. All those lines there, what they mean. Okay, so just real quick, let me show you. If you have a differential equation that looks like this, dy dx is equal to 2x over y. What that is telling you, the differential equation just by itself is telling us something. It's telling us what the slope is for any point in the xy plane, what the slope of a solution curve is going to look like for any point in the xy plane. Okay, so again, we're looking at that. The left side is telling us the slope, right? That's what the dy dx means, the slope of a tangent line, right? So if I just start picking some points that lie on the xy plane, any points. We'll pick a few that lie right around the origin. Okay, so for example, suppose I choose the point 0, 0. Well, 0, 0 is not going to be anything because if y is 0 in particular, it's going to be undefined, right? So undefined slopes typically are vertical, but 0 over 0 is totally undefined, so that one we'll just kind of skip that. But basically, if you have any y value that's equal to 0, this is going to be undefined, right? And we'll maybe agree with that. If y is 0, in other words, if we're along the x-axis here, we probably are going to have an undefined slope there, or we definitely are. So let's pick other points. Let's pick points that are along the y-axis. If it's along the y-axis, that simply means that x is 0, but y is something else, right? So basically what I have here, and I'll draw these with red, the slope lines are all going to be flat there, right along the y-axis. Everybody kind of see why that is? Because if I plug in any particular point whose y-coordinate is, or whose x-coordinate is 0, then that whole thing is going to become 0, and that's telling us that the slopes of any solutions are going to be 0 there. Okay. If you have, let's pick the point 1, 1. So if both x and y are 1, right? If both x and y are 1, then the slope there is going to be 2. You see, and so that's kind of steep. So what we're going to see there is a slope that's somewhat steep, like 2 right there. What about if x is 1 and y is 2? X is 1 and y is 2. Okay. then that means we're going to have a slope of 1 there, right? Because if y is 2, then those 2's would cancel. X is 1, it would just be 1, right? And so the slope would be less steep there. So maybe not as steep as the one way to put it. See? And then if we get bigger y's, you see, bigger y's, but the same x, then what's that going to do to the slope? Well, larger values of y mean the slope is not going to be as big. And so as we go up on this particular vertical line, we'll find that the slopes are not as steep the farther up that we go, okay? What about if we go in the negative direction? What if I have an x value of 1 and a y value of negative 1? Well, then I'll have a sort of steeply negative slope. So it'll be like this, kind of the opposite of that one there. Everybody see? And then if I go to -2, sort of the opposite thing happens. The slopes are still negative, but they become less negative. So we're going to see slope lines that are kind of like that. Okay, and that's maybe enough to kind of see what's going on. So if you imagine what a solution curve would actually look like here, it really depends on the starting value. So suppose I have a starting value that is, say, f of 0, or let's say y of 0 is equal to 1. That would mean that would be a starting point. And from there, all of my solutions would have to follow the solution curve, or the lines of slope that we're seeing here. So basically, the solution would have to follow these lines of slope. You can kind of see that as we go up, it would sort of flatten out like that. So coming back to letting technology do that whole thing for us, you can see that that's kind of tedious to draw all those little lines of slope, and maybe not so accurate either. Yeah, exactly. It kind of does look like metal shavings in a magnetic field. That's a good way to think about it. In fact, if you put a magnet underneath a surface and you put a bunch of shavings on it, you would see them all lining up in a certain way. That's kind of what's happening here, except they're not going to be lining up following a magnetic field. They're going to be following what the differential equation is telling us that they need to follow. Yeah, so you can kind of see that what I started to draw is sort of being matched here, right? And lines of slope are pretty steep down here at 1, 1. They get less steep as we go up like that. So do you kind of see where this slope field is coming from? It's coming, again, directly from the differential equation. You can even move this line around to see, like if you were to picture what a solution curve is going to look like, it would have to follow the line of slope. So the slope lines are kind of directing us where the solution curve has to follow. You see? If you move that around, you can kind of see where any particular solution curve would follow. Yeah, so anyway, you can play around with that if you want. On Desmos, just Google Desmos slope field, and that will bring you to this. Desmos slope field, the first thing on there is this thing here. And then you can see kind of the way that they enter it. They give a g of xy function on the left. That just takes the place of the derivative. In fact, is that right above there, right? Let g of xy be the derivative. And then they put g of xy in there. You can mess around with this stuff. That's all kind of whoever made this had to program all this. So it's maybe a bit tedious there, but really the only thing you need to worry about is like whatever differential equation you're going to plug in here, you would enter it right here. Okay, and then that would produce the slope field. So if you want to just see like the one for that problem that we just did, I said it was going to be a pretty big mess. I'll just replace t with x here, so it would actually be x times the secant of y, really, and then that would be then divided by y e to the x squared, so y times e to the power of x squared. Okay, so you can see the slope field that would be produced from that. Actually, it's not as bad as I thought it would be. It's just kind of a bunch of mostly horizontal lines. See how that one works? So the solution curves here would probably not be that interesting. In fact, any solution curve would probably just be a horizontal line that has a little bit of a dip right there. Oh, I guess it would actually turn around right there. So yeah, the solution curves are going to be these weird looking things. It would do something like that, looping over like that. So that's what slope fields tell us. Let's go back to the whiteboard again. The initial value problem in example 3 here. So again, remember what an initial value problem is. It's a differential equation that has with it an initial value. And the initial value then will allow us to figure out what that constant of integration is that we have on the general solutions for any of these differential equations. All right, so differential equation combined with initial value is known as an initial value problem. So yeah, we'll get y dy is equal to x sine x. And then we integrate both sides. Right side again is going to require the integration by parts. So u is equal to x, dv is equal to sine x dx, du is dx, and v is equal to negative cosine. So the integral there will become negative x cosine x minus the integral v du, that's actually going to become plus cosine x there. So we'll get minus x cosine x plus sine x. Okay, so that's the right side. Left side's pretty simple. We don't need to do anything fancy there. So this is going to be 1/2 y squared is equal to, I'm just going to reverse the order on that, sine x minus x cosine x. And then let's not forget our constant of integration there. I'm going to call it C1 for now, and then we'll multiply both sides by 2. Get y squared is equal to, basically all this is going to get multiplied by 2, so we'll have 2 sine x minus 2x cosine x plus 2c1, but I'm just going to call that c and make a new constant there where c is equal to twice c1. All right, so at this point, we would, if you want to solve this explicitly for y and not have an implicit function, we can still do that. We can take the square root of this thing. Now, remember that when you do take a square root, or when you have to solve an equation like this, you have to consider both the positive and the negative square root. Now, for this particular problem, since they actually give us the initial value up here, right? They tell us this. Now, if you look at that output there, how can we possibly get a -1 output by having a square root? Well, the only way that we can is by choosing, at this point, the negative root, right? You see what I'm saying there? We have to choose the negative root because of this initial condition here. All right, so the initial condition sort of told us which of the two roots we needed to choose. There's no way we can have an initial condition of y of 0 equal to 1 with this function that we have right here taking a positive square root, right? It has to be the negative square root. And I'm forgetting my constant again. There's the constant. So we have to have that. And then we can find c now, right? Because we know that y of 0 is equal to -1. Okay, so now I can plug that in. Y of 0 is equal to -1. That means this is -1, and x is 0. So 2 sine 0 there. 2 sine 0 minus 2 times 0 cosine 0. Well, that's just going to be a bunch of zeros, isn't it? And I'm sorry, I'm seeing that somebody actually did tell me about my mistake there. I just got a new monitor so I can see more stuff, but it's actually making things a little harder to catch because it's a little out of my vision here. So I'll try to pay more attention to the chat box here. Okay, so notice again, all of this is going to become 0, right? Sine of 0 is 0, 2 times 0, cosine of 0 is 1, but again, it's multiplied by 0, so all of that's just going to be 0. So we're going to have root c there, right? So we're going to have -1 equals negative root c. Well, we can square both sides of that and find that c must be equal to 1. Okay, so then the particular solution to this differential equation, in other words, the one that satisfies both the differential equation and the initial value, has to be this. Because remember, you can see that for basically any differential equation solution, you're going to have that plus c on the end. So for any value of c, you're going to have a different solution curve, right? And so in order to figure out which specific solution curve you're looking at, you have to have this other piece of information here, the initial value. All right, and so if we want to see this, I think this is probably worth checking out. Let's go ahead and graph both the function and this solution on the same slope field. So let me just show you kind of how that would work. All right, so we'll enter in that differential equation. All right, so here we've got x sine x over y. So there's the slope field. I told you that the ones that have trig functions in them are often produce pretty wild looking slope fields. Now let's go ahead and also graph that solution that we just got. Now let's just check, does this do what it, I mean, does this solution curve kind of follow both the slope field and have the given initial condition? In other words, is y of 0 equal to -1? It seems to be, right? Because look, it crosses right through 0, -1, right? And now look, if I move this little, I don't know what that is, a dot that sort of follows the slope field, look what it's doing, right? It's following the lines of slope, isn't it? Solution curve follows the slope field line. And so any initial condition would produce a different looking curve because it would have to pass through, a different point, right? So this particular one that passes through the point 0, -1 looks like this. So the point being, again, is that you can glean a lot about what the solution is going to look like without solving the differential equation. In fact, there's this method called the is that the Euler method, Michael, that has that solves differential equations numerically? Do you remember?
Yeah, Euler's method does that.
Yeah. Okay, yeah. So Euler's method basically doesn't even attempt to solve the differential equation. It just it uses something kind of like Newton's method, in that it will figure out what is the line of slope at a particular point, like say the starting value that you're interested in, and then it will just move it a tiny bit further. It'll sort of point the solution curve in the direction of the line of slope is pointing, and then it will stop and say, okay, now what's the new line of slope here? And then it'll point the solution curve a tiny bit in that direction again, and then it will sort of reiterate again and say, okay, what's the slope look like here? It'll just keep doing that, and it'll just like follow the slope field and produce a solution step by step, basically. So you'll at least be able to see what the solution curve looks like without even actually graphing it, or without even actually solving the differential equation. All right, so I hope that makes sense. Again, you'll see all this again in your differential equations class when you take that. Okay, so there's that solution. Oh, we're on problem 1 now. Okay, so let me see. I think that 1 is an example. I think right now I'm actually going to skip that for the interest of time. I'll go ahead and put Michael's solution up here just so you guys can see it, and then you guys can maybe look at it later if you want to. Let me try to find that solution. That's the one I'm talking about. The other two we'll probably have time to get through because we still have to talk about these application problems. Okay, so yeah, in that particular case, you could actually, if you wanted to solve for y, you could take the cube root of both sides, but you could certainly just leave it as y cubed equals as well. That's fine. Okay, and so now in math, we use the word orthogonal to mean perpendicular. It really is synonymous with perpendicular. They both mean the exact same thing. I'm not really sure why they decided to have a new word for it with math, but for whatever reason they did. And so just so you know, whenever you see orthogonal, just think perpendicular. It's the word for the same thing. All right, so orthogonal trajectories, what does that mean? Well, the best example I think that I've seen of this, about when you might be interested in maybe solving something like this, of course, this is a vastly simplified, the problems that we're going to do are vastly simplified, but if you were to maybe become a aerospace engineer, for example, you might be interested in this. What does the orthogonal trajectory have to do with that? Well, what I've attempted to draw there is not like a whale or anything. It's actually the wing, or an attempt of drawing a wing of an airplane. Okay, the shape that a wing of an airplane might take. Okay, and so it turns out that in aeronautical engineering, there is this concept of aeronautic potential energy. Okay, and what that is, it turns out that every surface that has some kind of fluid moving over it, like air, has a field that is associated with it. And I'm not even sure what they would call this field, but it basically runs perpendicular to all any point on the surface. This field would come out of that surface perpendicular to the surface itself. Okay, so I'm just kind of drawing what that field might look like for this particular surface, right? A bunch of perpendicular lines for every point on the surface. Okay, and so that field can be, you can have a formula for it or a model for it, right? There's a model that would say, if I have this surface, what is the field going to look like, right? And it's probably pretty simple to produce that because, again, all you have to do is just make whatever the surface is, the line has to come perpendicular to that particular area of the surface. And further, when you have airflow actually going over the surface, it turns out that the airflow actually passes through each of those field lines in a perpendicular fashion. So basically what that's saying is if you've got like wind coming at this thing, right? If the wing is moving into the wind, what's going to happen is all of the wind is going to cross through these lines of this field that's emanating from the surface of the wing, right? And so basically you'll see that the lines of fluid will pass through kind of like this in this fashion. And so what the aeronautical engineer is trying to do is, make sure that those lines, those wind lines, will pass in such a way to produce, the maximum lift, right? So there's other math concepts obviously going on in here as well. But what we might be interested in doing is figuring out, well, if I want to produce a particular, nice wind flow, what should the surface look like? What kind of surface should I actually have? And so you would maybe have a model of that aerodynamic potential energy field around the wing, and then you would want to find what solution curves would pass through in that perpendicular fashion. Okay, so again, this is just sort of motivating like why we might be interested in this. Of course, the problems we're about to do are far more simple than this, but if you did become an aeronautical engineer, this might be something that you would look at and be interested in, and you would probably be using a lot more sophisticated models than what we're doing here, but this is an intro. Anyway, so that sort of motivates like what's happening. Now let's see an actual problem where we're trying to find the orthogonal trajectories for a particular family of functions. Okay, so again, what we're going to look at here, we have in this case, family of functions. Okay, a family of functions. Why is this a family of functions? Because that k is a constant, and as you vary that k, you would produce a different curve, right? So for example, if k was 1, you would have y squared equals x to the third. You could solve that for y if you wanted to. You could graph the solution curve. If k was equal to 2, you would have a different looking solution curve, right? So basically one solution curve for every value of k. So this produces infinitely many curves, right? And so we call this a family of functions or family of curves, okay? And what we're trying to do is find another family of curves that will cross this family of curves in this orthogonal way. In other words, any of the curves that we're looking at and this new family of curves we're trying to draw, we will see that those new curves will cross all the old curves in a perpendicular fashion. So how do we go about approaching this? Well, the first thing we want to do is find a differential equation that matches that family of functions. Okay, so find a differential equation that will match that family, or that will produce this family of functions. So how do you do that? How do you find a differential equation? And remember that what a differential equation will itself produce is a slope field, right? And so basically what I'm trying to do is find the slope field that will match this particular family of functions, okay? Well, the best way to do it is to just differentiate both sides of this. So we're going to do that, differentiate both sides with respect to x. Although you could just as easily differentiate with respect to y, it really won't matter, as we'll find out. So we're going to differentiate here just with respect to x. This is called implicit differentiation, if you remember from your Calculus 1 course. In fact, we're doing that right now in Calculus 1. But So for here, we have to remember how that works, right? So if I differentiate y with respect to x, I get 2y dy dx. That's from the chain rule again, if you remember that from your that one class. This is 3kx squared. Okay, and then the next step is to solve this for dy dx. In fact, this, if you remember your Cal 1 implicit differentiation steps, this is exactly what we're doing. We're finding dy dx for this particular equation. Okay, and so I solve for dy dx, and I get 3k x squared over 2y. Okay, now it turns out that in problems like this, we don't really want to have that k there, the constant, so we need to eliminate it. Eliminate k. How can we do that? Well, we can put k in terms of both x and y by solving that equation, the original equation for k. Okay, so we're going to solve that for k. K is equal to y squared over x to the third. Okay. Then I'll plug that into the differential equation. So I'll get dy dx is equal to 3 times k, which we now know is y squared over x to the third, x squared over 2y. Okay, so now that's going to cancel this, and that will just become a first power, right? So what I'll end up with here is 3, well, let me write it like this, 3y squared over x, and then this I can call it over 1, and I can say this is multiplied by 1 over 2y, and then that cancels that with that, and so I'm left with what, 3y over x, 2x, 3y over 2x. Okay, everybody see kind of what I did there? I differentiated both sides with respect to x, and then solved for dy dx, and then eliminated k by going back to the original equation, solving it for k, and plugging it in, okay? And so what I have now is this. I've got a differential equation, dy dx, on the left side is equal to 3y over 2x. This is a differential equation, right? It has a slope field. In fact, if we were to go back to that Desmos slope field grapher, what we would find if I were to plot the slope field for this differential equation, and then I were to plot a few members of this family of functions here, what do you think I'd find? Well, since we got that differential equation from that family of functions, what we would find is that all of those solution curves for all those various, oh, sorry, I was going to sneeze, for all those various values of k would match the slope field produced by this differential equation. Exactly. Okay. Any questions about what we're doing so far? Now, remember that orthogonal means perpendicular. So this slope field, the slope field produced by that differential equation, will match the functions that we started with. But we actually don't want that slope field. Which slope field do we want? We want a slope field that has slopes that are compare how to this slope field. We want them to be perpendicular, right? And so how do you make a perpendicular slope from a given slope? You guys remember that? Again, just thinking back to maybe your intermediate algebra class. If I have a given slope and I want to find a slope that's a line that's perpendicular to that, what do I do to the slope? You guys remember? Do the
invert it.
Invert it. We want a slope that's perpendicular to the original slope, but that slope is given by this differential equation here. Invert it and do something else to it, right? What's the other thing you do? Negative, exactly. flip it over and make it negative. And so that's what we're going to do here. We're going to take that slope, the slopes of the original function, the family of functions, and we're going to invert it and make it negative. Flip it over and make it negative. And that will then produce a new slope field that will, what will be true about all these new slopes? Well, they'll all be perpendicular to the slopes of the original one, okay? That's the idea. Now, what do we have here? We have a new differential equation, right? This is definitely not the same as this one, right? And so now I have a new differential equation, which, guess what? It's separable, right? And so now we can solve this new differential equation by the method of separation of variables. Okay, makes sense, kind of the procedure here. And so separation of variables tells me this is going to be 3y dy is equal to negative 2x dx. We integrate both sides of this. So we're going to get 3/2 y squared is equal to negative x squared plus some constant. Now we can, let's just kind of take a look at what this is that we've just produced here. The differential equation itself wasn't that difficult to solve. We didn't have to do any parts or anything like that. But look at what we've got here, and maybe we can even rewrite it in a slightly different way here. Suppose I write it like this instead: y squared. I'm gonna write it in kind of a weird way, but you can see why I'll do this. Y squared over 2/3, and if you see that is equivalent to what I have there, right? Plus x squared is equal to c. And now I'm just going to do one more thing here and say, what if I write it like this? What if I write it as x squared over c plus y squared over 2/3 c is equal to 1. Now, why the heck would I want to write it like that? Does this look like anything that you guys have seen before? Maybe in your pre-calculus class or something like that. Hyperbola. Is it a hyperbola? Close. Ellipse, exactly. It's an ellipse. In fact, it's not just one ellipse because we have that c there. What is it? It's a whole bunch of ellipses, right? It's a whole bunch of ellipses. So let's just take a quick look at Desmos again. I'm just going to show you how this is going to work. And we don't even need any fancy Desmos for this one. I'm just going to use the regular Desmos website for this. What am I trying to graph here? Well, I'm going to graph a few members of that original family of functions. So let's see, y squared is equal to, let's start with just 1, k being 1. So x to the third. Okay, so there's one member of that family of functions. Let's check what happens if we do a different member, maybe a few different members of this family of functions. I put 2 in for k. So we can maybe get a picture of what these are going to look like. How about a negative one? Y squared is equal to negative x to the third. Y squared equal to negative 2x to the third. Okay, so again, you kind of see what's happening here. This is just a bunch of different members of the original family of functions that we looked at, okay? We just do 2 others on here. All right, so that's probably sufficient just to see what the family of functions of that original, the given family of functions actually looks like. Now let's take a look at the family of functions that we got for our solution. We'll kind of see, does it do what we want it to do? What was that? It was x squared. I'm going to use the one that's just equal to c here. I'll just put 3/2 y squared, and I'll put the plus x squared. Now, this has to be equal to various constants, so I'm going to put 1 first. Okay, so that's maybe the first member of this family that we're going to graph. We can do others. And now, in particular, just notice how these this new family of functions is crossing the old family of functions. See that? Look closely. How are they crossing each other? At every point, how are they crossing each other? At right angles. You see that? So what we've done here is we've found, if we started out with this family of functions that kind of looks like parabolas but isn't, and we're asking what family of functions are orthogonal, well, we now know it's a bunch of ellipses that are the ones that are going to cross through this other family of functions in this perpendicular fashion. Okay, see how that works? Pretty interesting, huh? And so this is a nice little application of differential equations and separation of variables. Okay, I'm gonna let you do one of these real quick, and then we'll talk about the mixture problems. Okay, so try to work on this. I'll give you just a few minutes to do this, maybe 5 minutes, and I'll show Michael's solution when you're in just in a minute or two here. Okay, so try to work on this for just a few minutes, and then we'll come and talk about the mixture problem. So you're going to work on problem 2 now, the one that says x squared plus 2y squared equals k squared. Just a quick word about that one. Notice that on the right side, that k is a constant, right? And so for this particular problem, the one you're about to do, when you differentiate that thing, the k is going to disappear immediately. So you don't actually have to take that step where you solve for k, if you see what I mean. Because taking the derivative of this problem, k squared is a constant by itself on one side. Differentiating it makes it go away immediately. So we don't have to bother with that, getting rid of the k, okay? So keep that in mind while you're working on that one. Okay, so again, first step is just to differentiate both sides of this implicitly with respect to x. So that's what Michael's doing first here. Implicit differentiation. Again, notice that k squared goes to 0. Move or solve for dy dx. You get this thing here. Flip that over and make it negative. Right, so that's what this step is here. New slope. Flip it over, make it negative. Solve that new differential equation by separation of variables. So as you can see what happens there, basically you get a 1 over y on one side, 1 over x on the other, so you just get natural logs all over the place. To solve that particular equation, you have to exponentiate both sides, right? And so that means you get this on the right side, and then notice what Michael's doing there. That's e to the power of ln x squared, right? And so if you split that up, that actually can become, you can actually write that as, e to the ln x squared. Yeah, then you can multiply. And then notice the e and the ln cancel. That brings the x squared down, and you've got e to the power of c1 there. And then you can define a new constant. You can say that c is equal to e to the power of c1, and that produces this here. And so what is that family of functions? That would be a bunch of parabolas, right? A bunch of parabolas opening up and down depending on what the c value is, okay? In fact, Michael, you wouldn't even need to put the plus or minus on there because of the c could take on any particular value there, right?
That's true. That's true. This is that one where I was only getting the upper half.
Oh yeah, so that's why, right? Because the absolute value part, yeah.
Yeah.
But yeah, again, c can be any positive or negative number, so that means that this could be up or down. And if you think about the original family of functions here, right? What is this? What was that to begin with? Well, if you divide both sides by k squared, then that is also that's a family of ellipses. So what we have here is a family of ellipses whose orthogonal trajectories happen to be a family of parabolas instead of that. Then the last problem is kind of like a x to the 3/2 power or something like that. But anyway, if you were to graph both of these families of functions on the same set of graphs, same set of axes, you would see exactly the same thing that we saw last time. Starting out with a bunch of ellipses, and then those parabolas would intersect those ellipses in a perpendicular fashion at every intersection point. All right, so we'll come back to that solution of that other mixture problem. But for now, let's do the example mixture problem. Okay, so you can read through the problem and kind of see what's going on with it. These are kind of tricky, these mixture problems. Maybe a little bit harder than the orthogonal trajectory ones. Okay, it says a tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute. Solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt is in the tank after t minutes and after 20 minutes? All right, so I can almost guarantee that you will probably get problems like this in your differential equations class as well as what you're seeing here. But those will actually be a little bit harder. So like you can notice on this one where the water is going out of the tank at the same rate that it's coming in. That might not be the case in like the differential equations test. The water might be exiting faster than it's entering or something like that. All right, so anyway, here we're not going to do that. We're just going to do stuff like this. So how do we deal with problems like this? The first thing to do is to just define a variable. We're going to let y be equal to the amount of salt at any time, or let's just say at time t. So the amount of salt, pure salt in the tank, not a mixture or anything like that. This is just the amount of salt, because it's actually, the question is how much salt is in the tank, right? That's what they're asking for. And since that's what they're asking for, that's probably what a good thing to make this variable be, the thing that they're actually asking for. Okay. Now, what do we know is happening in this particular situation? Well, we know that the amount of salt is changing as time goes by, right? There's some salt going in, and then there's some salt going out. Potentially, there's some salt going in, not in this case, but potentially there is. And so we know that the amount of salt is changing. And so what we can say, we can write a differential equation that sort of models how it is changing over time. Okay, so the rate of change of salt is what I'm writing on the left side. Rate of change of salt at any time. And the way that we approach it is we say, well, how much salt is actually going in? And we just write a little equation there for that. And then we have to subtract off of that how much salt is going out. So minus the amount of salt that is going out. So this is a good way to start these, is just to say, let's do it step by step. How much salt's going in? Come up with an equation for it. How much salt's going out? Come up with an equation for it. Subtract those two things. All right. So how much salt is going in? Well, it says that we're adding pure water, right? So no salt is going in this case, 0. That's kind of easy. In the second problem, you'll see that's not the case. But here, no salt is going in. How much salt is going out? Well, let's see. We probably want some dimensional analysis might actually help here. We've got how much salt is in this tank at any time. Well, we said that there's y kilograms of salt at any time, right? Y kilograms at any time. I'm going to use the units so that we can kind of figure out maybe to make them match to the units on the right. Then it is exiting at a rate of 10 liters per minute. Or no, I'm sorry. Yeah, that's right. It's exiting at the rate of 10 liters per minute. So times 10 liters per minute. But really, we kind of need a concentration here. So it's actually y kilograms of salt per 1,000 liters, right? That would be the concentration of salt at any time, okay? And if you kind of look over here on the left side, what do we have here? We said that y was the amount of salt. So the units of y should be kilograms, right? So on the numerator here, we have kilograms. And on the denominator here, what are the units that we have? This is measured in minutes. So kilograms per minute is what we see on the left side, right? dy dt is kilograms per minute. We should see the same units on the right side, okay? So if you kind of follow this procedure I'm doing here, this is the concentration of salt at any time, y in kilograms per 1,000 liters. And then how fast is it leaving? It's leaving at a rate of 10 liters per minute, okay? Now look at what happens to the units here. Those are going to cancel, right? And what are we going to be left with here? Kilograms per minute, right? Which matches the units that we see on the left side. That's what you want to see. The units on the right side have to match the units on the left side, okay? So there are differential equation. Now getting rid of the units, just verifying that we've matched units on the left side and the right side. No salt was going in. We do have that minus sign though. So minus 10 over 1,000 is 1 over 100, right? So 0.01 y, and that's it. So this is our differential equation then. Pure water entering at 10 liters per minute equals 10 liters per minute. Not 10 liters per minute of salt, but 10 liters per minute of mixture of salt and water mixed together. Okay, so that's like a concentration of salt. What we're got. Okay, cool. And it drains out at the same rate. Yeah, exactly. Right. So the mixture is what's draining out. All right. So this is the differential equation then that we need to solve. This differential equation itself, in this case, is actually pretty easy to solve. This is a separable differential equation. We can just divide both sides by y and then multiply both sides by dt. And so there we go. There's our separation of variables. On the left side then, we'll get, well, let's integrate this. On the left side, that's the natural log of y, and I'm not bothering with the absolute value because we're not going to have negative amounts of salt in here, so we don't care about that. And then on the right side, negative 0.1 t, and then we have our constant of integration there. Again, I'll call that C1. Now we exponentiate both sides. That's making e the base of both sides. E and the ln will cancel, and we'll be left with y is equal to e to the power of negative 0.01 t plus C1. And then remember, on the right side, you can always use our properties of exponents to rewrite this like that. And then you can define a new constant where c is equal to e to the C1. And so you get y is equal to c e to the negative 0.1 t. Again, where c is equal to e to the power of C1. Okay. Now there's one piece of information we haven't used yet, right? And in fact, it was the first thing they even said on there. Well, the second thing, I guess, that there are 15 kilograms of salt already in the water, right? And since they are pouring in pure water, what should we expect to happen over time to the amount of salt? Well, if they're pouring pure water to stuff that's briny, already got a bunch of salt in it, as time goes by, what's going to happen to the concentration of salt? Well, it's going to go down, right? And then eventually, over a long period of time, there's not going to be any salt in there, right? Because eventually all the salt will get drained out. So, however, we do need to use that piece of information, y of 0. How much salt was in there at the beginning? 15 kilograms. So y of 0 is equal to 15. This is what's going to allow us to find that k, or sorry, the c in this case. So we could say 15 is equal to c e to the 0, right? Negative 0.1 times 0. 0. E to the 0 is just 1. That just means that c is actually equal to 15 in this case. Okay, and so the equation that we're after is this: y is equal to 15 e to the negative 0.01 t. Okay, that is our particular solution to this initial value problem. So that's the solution. Then they further ask us how much salt is going to be there after t minutes. Well, we just answered that question. After 20 minutes, so we can answer part B now, right? Yeah, after 20 minutes, y is going to be equal to, we'll just say y of 20. This is all measured in minutes. Yeah, okay, so 15 e to the negative 0.01 times 20, and what is that? 12.3 roughly. So after 20 minutes, the concentration will have gone down to the point where there were 15 gallons or 15 kilograms dissolved in there at the beginning. 20 minutes goes by, we'll see that now there's only 12.3 kilograms of salt left in there, dissolved into the water. Okay, and as time goes by, you can picture what the graph of this function looks like, right? That's an exponential function with a negative exponent, right? So that's a decreasing exponential function. So as time goes by, what we would see is it would have started at 15, right? That's y of 0. And then since it is a decreasing exponential function, we should expect to see this type of behavior as time goes by. That it approaches 0 asymptotically. All right, well, the next one is a little bit tricky because if you can just read through it real quick if you want. It starts out with same saying there's 1,000 kilograms of water. Now in this case, there's just the initial condition is that there is no salt at all in the tank. So y of 0 is 0, pure water it starts with. But now what's happening? Now we're pouring in brine that has salt in it. Okay? That has a given concentration of salt in it. In fact, two different ones are pouring in, right? One pouring in at one concentration, another's pouring in at another concentration at a different rate. But if you see that the total rate of water input is actually 15 liters per minute, right? Because one of them is pouring 5 liters per minute, one's pouring at 10, and then it says that it pours out at 15. So it turns out that the tank is always going to be the same level. And so the question here is, well, how much salt is going to be in the tank at any time? In other words, we need to come up with some model, some sort of function that will tell us y of t is equal to whatever, how much salt is in there at any time. And then how much is in there after an hour? And then I would add another question on there. Is there some kind of equilibrium, in other words, after a very long time, is it going to sort of even out so that there's a constant amount of salt in there? So that would be maybe how much salt is in there after a very long time. So with all this in mind, what you might want to do is, when you're thinking about how to do this, same idea. You would say, let's let y be equal to the amount of salt at time t. And say, okay, well, we know that that amount is going to be changing. So we've got a dy dt on the left side. And it's going to be changing in such a way that we've got some salt coming in. We've got some salt going out. And so how much salt is going in? Well, for that, you can think about, again, thinking about what units we should be seeing on the left side there. We've got liters and minutes, right? Well, actually, sorry, kilograms and minutes, right? Because we said y was the amount of salt. So this is kilograms on the numerator and minutes on the denominator. And so when you're trying to think about what is going to go here, just make sure that it ends up being kilograms per minute after everything else cancels out. So thinking about like, there's two different amounts going in, right? The units, notice, are kilograms per liter. And then you have the rate, liters per minute, kilograms per liter times liters per minute. Kind of think about what that might be and go from there. All right, let's go through the procedure on this one. I'm actually going to probably do this slightly differently than Michael did it, but I'm going to at least start out with what we've got here. So taking a look at this, it says, yeah, so here, rate in, salt in. Okay, there's two of them that are coming in, right? What I was trying to sort of hint at before is that you've got the concentration, 0.5 kilograms per liter, and the rate, 5 liters per minute. Notice that when you multiply those together, what happens? Liters cancel, and what are you left with in your units? Kilograms per minute. That's exactly what you want. So that first input is going to have that concentration of salt in it, 25 kilograms, or the rate at which the salt itself is actually going in, 0.25 kilograms every minute. The second one, similar, very similar, right? 0.4 kilograms per liter times it's going in at a faster rate, 10 liters per minute. But again, liters cancel and you're left with kilograms per minute. So that's the amount going in on the other one. So, and then the amount going out is a little bit different because, see, these ones we actually know the exact concentration, right? At any time, the concentration is the same. Now, the out is a little bit different because the concentration that's going out at any time is going to be different at any given time because the amount of salt is constantly changing. So all we can do as far as concentration is just, we know that there are y kilograms, I'll just put a kilograms right there, y kilograms of per 1,000 liters, right? So that's a concentration also, right? Kilograms per 1,000 liters, that's a concentration. And then multiplied by the rate at which it is leaving, 15 liters per minute. Again, notice liters cancel, and we're still left with kilograms per minute. Okay, so everybody kind of sees a little bit different in how you have to treat the salt going in versus the salt exiting. Putting those together, that's the salt in right there, minus the salt out. Salt in minus salt out. And then simplifying all that stuff, you get this differential equation right here. And Mike went ahead and found a common denominator and combined these two things. Which is, in fact, that is a great thing to do. I never thought of doing that before, but yeah, that's a good thing to do. So yeah, find a common denominator, add them together, and put it over 1,000 like that, I guess. And then you get this, the differential equation, I think. Yeah, so this is the differential equation that you have, right? dy dt is equal to that. Okay, so if that's the differential equation, that dy dt is equal to this circled thing that I just wrote there, then you can divide both sides by 650 minus 15y, and I could see this for the left side, and then you can just leave the 1 over 1,000 on the right side, and I could see that. Okay, and then that left side can be done by a substitution, which is what Michael's doing right there. That's a substitution. U is equal to 650 minus 15. U is the denominator, basically. So du is minus 15 dy. You have to divide by that minus 15. Hence this negative 1 over 15 there. Right side, pretty simple integral. There's no variables there. It's just 1 over 1,000 dt. So the antiderivative there, you just got to put a t on it. Get that. And then you have to have the plus c1. Antiderivative, left side ln. That's what that is with the minus 1/15 there. Right side, we would want to multiply both sides by 15 there to get rid of this, by negative 15 actually, which then produces this and a new constant where C2, I'm assuming, must be negative 15C1, yeah? Negative 15C1.
Yeah.
Yeah. And then what do you, oh yeah, u was 650 minus 15, so we're going to exponentiate both sides, right? Got to get rid of the ln there, so you make e the base of both sides. The u was this quantity here, so that's why we get this right there. Again, with the e to the c2 power there, you can define a new constant. C is equal to e to the power of c2. And so what do we end up with at the end of this thing here? 15, well, then we have to solve for y, so we got to subtract the 650 from both sides and then divide by 15. And doing all that, basically this is just algebra at this point. Doing all that, you get this. So this is the general solution to this differential equation. Okay, that's the general solution. Then we also know that y of 0 is 0, right? Y of 0 is 0, because it says that it started with pure water, right? Y of 0 is 0. So we can plug in 0 up here for t, plug in 0 for the left side here, allows us to find c. There's the c. And so look, here's our final solution here. This final answer, and then you can answer the question, how much is going to be in there after an hour? Plug in 60, that'll be 25 kilograms roughly, 25.7. Now I would also add one other question on here. How much is going to be there after a long period of time? Now that you can answer, so after a long time, and I say long time, that's kind of subjective, but long time just means, like, mathematically speaking, how would you answer that question? You would take a limit as t goes to infinity of that function y of t. But that limit's pretty simple, because if you look at the function that we have here, this one right here, that is a negative exponent, right? And so when I let t go to infinity, what's going to happen to that entire term? Since it's negative exponent, all of that just goes away, right? That's just going to go to 0. And there we go. That's the limit, 130 over 3. So after a long period of time, it is actually going to stabilize to a certain quantity of salt in there. And 130 over 3 is, what is that? 43.3 kilograms of salt after a long time. So basically, if you were just to leave this contraption running for a long time, pouring the one salt in and the other one as well, draining it out at that constant rate, after a long period of time, you would find that it does stabilize to this quantity of 43.3 kilograms of salt. So basically, as time goes by, it starts at 0, it increases exponentially, but then levels off, and then we'll have that horizontal asymptote at 43. So it is definitely a increasing exponential function, but it's actually, if you look at the way that it's written here, it's actually flipped both horizontally and vertically because we got that negative there and the negative up in the exponent. So it's like a flipped exponential function with a horizontal asymptote at 43.3.